This is an NPN transistor. It has 3 terminal, collector C, base B, and the emitter E. I have indicated the current direction with the red color. The collector current is mentioned by IC, the base current IV, and the emitter current is IE. Considering this is in common emitter configuration. The voltage between the terminal base and emitter I have denoted as VVE, and the voltage between the collector and the emitter I have denoted this is as VCE, and the voltage between the terminal collector and base I have denoted this one VCB. A transistor always follows KCL, that means Kirchhoff's current law. In that case, the emitter current IE equal to the sum of base current and collector current. Ratio of collector current IC and the base current IV is called the transistor's current gain, and it is denoted by beta F. And beta F is equal to collector current divided by base current. That means IC over IV. Alpha F, which is the ratio of collector current IC and the emitter current IE. And from equation number 3, you can find there is another form of equation just like this. If you divide the numerator and denominator of this equation by IC, and then you can see the equation is being changing like this, and finally you will get the equation is alpha F equal to 1 over 1 plus 1 divided by beta F, and this is beta F over beta F plus 1, and then finally alpha F equal to beta F over beta F plus 1. Operation. A transistor can operate in 4 different types of operational mode based on its biasing. So those operational modes are forward active mode FA, cutoff mode CO, saturation mode SAT, reverse active mode RA. The cutoff region, cutoff mode of a transistor is just this, the flat line, and the reverse active mode is just indicating in this line, and this is the saturation region. Forward active mode. In forward active mode, the transistor behaviors are very interesting, and most of useful operation of a transistor is in forward active mode. In this mode, the base emitter junction is always forward bias and the collector emitter junction is always in reverse bias. So just like this, this is the collector emitter voltage. You can see this for a NPN transistor, it is in reverse biased collector emitter, and base emitter junction is forward biased. In forward active mode, a transistor can work in 3 operational regions. One is cutoff region, another is forward active region, another is saturation region. Before I go through for these three regions in details, I want to mention some conditions for a transistor for the common emitter configuration. And some conditions are: a transistor will not be fully conductive if it is not provided 0.7 volt on its base emitter junction. PV on means the transistor will be conductive fully in 0.7 volt. It starts being conductive from 0.6 volt. VBE, edge of conduction, is equal to 0.6 volt. A transistor reaches in saturation when it gets 0.8 volt on its base emitter junction. Cutoff region. When a transistor is in cutoff region, it shows the collector current IC equal to 0 and the voltage between collector and emitter is equal to the supply voltage, whatever voltage was in reverse biased or biasing voltage. IC is the collector current flowing for applying VBE. This IC is we mentioned as small IC. This is because of the applying voltage VBE, whatever current is flowing from C to E. So if you apply some voltage in VE in base to emitter junction, and for that reason whatever the current is flowing from collector to emitter, that current is IC. So it means no current will flow from collector to emitter in cutoff region. In that cutoff region, the transistor behaves just like the diagram on the left side. See, open, open, open. So this transistor in cutoff region, it will act like an open circuit. In that situation, whatever voltage applied on VCE, whatever voltage you apply on collector to emitter, the transistor will not pass any current. That means the collector current IC will be 0 because the base emitter voltage is less than 0.6 volt or no base voltage. And you can see the graphical representation of this collector current IC versus VCE. Now we are moving to forward active region. What behaviors a transistor shows to us in forward active region? Let's have a look. In forward active region, in this region, the collector current will be greater than 0. That means some currents must be flowing from its collector to its emitter. In the edge of saturation, the transistor VCE will be greater than the voltage VCE edge of saturation, that means 0.2 volt. Here VCE is the voltage drop across CE terminal for applying VBE. Yes, for applying VBE, whatever voltage drop across this collector emitter terminal, that is VCE. So VCE is greater than VCE edge of saturation. Edge of saturation voltage is 0.2 volt. That time in forward active mode, you will find the VCE is greater than 0.2 volt. If you find the VCE is greater than 0.2 volt, you can say the transistor is in forward active region. See this model, the exact model of this forward active region. It behaves just like this. In this base emitter region, there is a little voltage, small amount of voltage, 0.7 volt, which is the transistor on voltage, and this is the mechanism here. And the collector current in forward active region, it's the product of beta value and the base current. Forward active region exists from VVE on equal to 0.7 volt to VCE equal to 0.2 volt. As long as VCE drops down to less than 0.2 volt, as long as VCE drops down to less than 0.2 volt, the forward active region turns to saturation region. You can see the graph here. Saturation region. In saturation region, the collector current IC is greater than 0, and VCE, the changed voltage VCE, is greater than 0 but less than edge of saturation voltage. That means less than 0.2 volt. In saturation region, collector current greater than 0 and base emitter saturation voltage is 0.8 volt, and the changed voltage VCE is greater than 0 but less than its saturation voltage. That means 0.2 volt. In saturation, what is happening? In saturation, the beta value is less than the beta value of forward active region. Why? In saturation, the collector junction becomes forward biased. The collector base junction, we have seen previously, we said for forward active region the collector base junction must have to be in reverse bias, but without changing physically in saturation region, this junction by itself turns to forward biased. That means NPN. If you check with the multimeter in that junction, you will see this junction turns in forward biased in saturation region. And for that reason, some fraction of current of IB, and then IB it just gets separated, or it just splits in two parts. One is going in that direction and another will go in that direction. That's why it's gonna lose its amplification current IB, input current IB, because this junction is turning in forward bias. That's why it's just losing the amplification input current. So that's why the beta value is less than the beta value in forward active region. This is the graph here. For saturation region, the collector emitter voltage is less than 0.2 volt, and we can pick up one point from this region, saturation region, say this is less than 0.2 volt, and in that case the IC saturation current is showing in this diagram.